Hi everyone, and welcome to my presentation on the uncertainty propagation in approach GN&C using differential algebra. I am Kostas Konstantinidis and we worked on this with Dario. In the future there will be ambitious missions to accurately and safely approach a body, like for example active space debris removal, asteroid landing, and very accurate pinpoint planetary landing. And of course, GN&C is critical to these missions, and in particular, we can say that there's three sub-functions in GN&C that will be critical: guidance, navigation, and hazard detection and avoidance, with their own functions. But of course, we will need to, when designing the systems, we need to validate their reliability and their accuracy and their performance in general. And we do this often by using models of these systems and propagating uncertainties through these models. And of course, these uncertainties are things like coming from the environment, from the sensors, from the actuators in the system, and of course the models are non-linear, and this gives you output uncertainties. And we do this uncertainty propagation currently either by linearizing the models, which is has a low computational burden but is not as accurate, and the usual Monte Carlo analysis, which is computationally intensive but very accurate. So it would be nice to have an intermediate solution, so let's say a compromise between the two, which is accurate but also computationally efficient, and we argue here that differential algebra offers this alternative. So a differential algebra is an algebra of truncated Taylor polynomials, which in short, having a dynamic equation here propagating the initial state to the final state in a system, you can define the initial state as a so-called G-dual variable, an uncertain variable that you want to study. Then you expand this function, the dynamic function, to a Taylor polynomial, and you can evaluate then the G-dual variable through the Taylor polynomial instantly, essentially, so in a very cheap computational manner. And then you can do, as you can imagine, a differential algebra-based Monte Carlo where you evaluate many initial conditions. You can do the so-called polynomial bounders method, where you start from your the bounds of your initial conditions and you just propagate the bounds, and then you immediately find the bounds of the final conditions. Or you can invert the Taylor polynomial and start from the bounds of the final condition, so the requirement, let's say, propagate them backwards instantly and see how the initial conditions behave, let's say. So this method, as we said, can be more computationally efficient than classical Monte Carlo, but this is to be determined per case, as we will see in the following. So to investigate the application of differential algebra to GN&C, we had here a case study on a simplistic pinpoint landing on an asteroid, on this blue potato here, which is a model of asteroid Psyche. You can see here in red the trajectory, the nominal trajectory in the inertial coordinates, and in green in the body frame. So for the guidance and control function, we made a GECNet, which is a neural network based method, and essentially it's a neural network that maps initial conditions to controls here, and as any neural network method, it needs to be trained on a database. You can see here the database of optimal trajectories that we generated to train it. And for navigation, the navigation function, we are working on it currently, and it will be added in the next iteration of this work. So here we'll focus on the guidance and control function with the GECNets. So to demonstrate the application of differential algebra for GN&C analysis, as we saw before, the point here is to offer a computationally efficient but still accurate uncertainty propagation method. So going back to the slide about differential algebra, you will remember this. So the steps here is to define as your dynamic model here the GECNet, the GN&C model of interest, in this case a GECNet, and any uncertain parameters you want to study, you want to see how they behave, you can define as G-duals and then propagate them through the Taylor polynomial that you expand of the function, and then you can do, for example, DA-based Monte Carlo analysis. And here we will show an example about an uncertain initial state, where we propagate a grid, a 3 by 3 by 3 grid of initial starting points perturbed in trajectory, perturbed in position, and we propagate them to the final point right here. And here you can see a zoomed in version of the final point. So you can see the lines represent the usual floating point propagated trajectories, and the points represent the Taylor polynomial estimated final points. So in this case, you can see that there's even for an order of 1, a Taylor polynomial of an order of 1, you can see that these points coincide quite well. And to further study the sensitivities of, for example, the order of the Taylor polynomial, we define here an error metric, which is the average of the errors between these pairs of floating points and G-duals final points. And we can see here the sensitivity, for example, of this error to order. So for higher order polynomials, you get higher accuracy, up to centimeter accuracy for position, and millimeter, sub-millimeter for velocity, millimeter per second. But then you get diminishing returns at order 3. And here we saw the sensitivity to initial conditions. So if you start further away from the nominal point and propagate in G-duals in a Taylor polynomial, you get less accurate results. Of course, it's going to be more accurate near the initial starting points. And here we saw the computational efficiency of G-dual propagation versus floating point propagation. This metric tau is the relevant efficiency of G-duals versus floating points, and below this dotted line, G-duals becomes more efficient by that order of magnitude as you go up as you have more and more samples or trajectories propagated. So for a polynomial of order of 2 that we saw before was adequate for from an accuracy point of view, you can see that the break-even point is at 1,000 trajectories, and then G-duals becomes much more efficient, orders of magnitude more efficient if you want to propagate many more trajectories. Yes, this was my presentation. Thank you very much for your attention. For this work we used our in-house open source software, PyCap, Pygmo and PyAudi. Thank you very much and have a nice day.